Good morning, afternoon. I can't even tell what time of day it is. Okay, I want this one and this one. Feels like the crowd's thinning out. It's not a good sign. Let's see. I think we were doing. Oh, go back, go back. There it was. Okay, that's where we need to be. And I think if I do this. Oh, I have to end their class. Oh, I didn't end that class. Let's see what I'm doing. Oh, okay. That's not what I wanted anyway. All right, let me turn my chat on. See what's going on with y'all. All right, let me open up attendance. How many different things? Why does Spotify open? It's like Spotify is always open when I don't understand why. I don't need this one. So I'm going to put that right there. And I think that's all I have. How y'all doing? Good? It feels very empty today. I don't like empty classes. I like them to be full. Not that I know of. That might change, but not that I know of. At least it's not Monday. That's a good thing. That's true for our class every day, right? It's not Monday. Never Monday. And I forgot my jacket today, and I am freezing. All right, y'all ready for y'all joke of the day? Cannot disappoint. I don't know. This one's pretty corny, though. Did you hear about the mathematician who's afraid of negative numbers? He'll stop at nothing to avoid them. Okay, that was pretty nerdy. That was pretty nerdy. I'll admit it. I liked it though. Okay, so before we start on all of our stuff for the day, my reminders for you are we have our exam next Tuesday on chapters 5, 6, and 7. 5, 6, and 7. Okay. Our exam's on Tuesday, and then drop day is on Wednesday. I promise you that you will have your grades by the end of the day on Wednesday, so that if you are contemplating dropping, you have all the information possible by drop day, okay? Chapter 6 homework was due last night, right? Y'all all did y'all homework? So I ported grades over. I didn't open the chapter 7 homework until after I pulled grades over so that nobody could start on 7 before I brought grades over and then have these weird grades in Moodle. So chapter 7 is now open, and your grades in Moodle should have all of your My Lab and Mastery homework, like points inside of it, okay? It doesn't? It doesn't for you? Okay, send me an email and I'll look at yours, because everybody should be now. It's always something with Moodle. It's always something with Moodle. And Moodle's been running real slow today. I don't know what's going on with it. I don't know if y'all noticed that, but it's a challenge today. You can what? It wouldn't let me in at all. You go off. Oh, yeah. See, something's going on with Moodle today. I'm not sure. So maybe check your grade tomorrow instead of today. Your show's there. I don't know. Give Moodle 24 hours and hopefully some of the stuff will clear up. I did on the new chapter 7 homework, I did the same thing that I did on the last one, where I gave y'all some bonus points. I gave y'all some areas for bonus points. So they have some really cool little tutorial things that you can go through. And so I made those bonus points. So they'll definitely help you bonus point wise, and they'll help you, you know, so you know what you're doing. All right. So chapter 7, section 1 and 2, you should have watched for today. And they were kind of long. They were long. It was kind of a long 2 sections. I'm sorry about that. I can't really control it. But I also posted for 1 and 2, like I forget of all the things I want to tell you. For 1 and 2, because it was so long, I just incorporated a few problems as we went and then said, okay, your in-class problems, I did them as a separate video and you can watch them if you want to. Up to you, you know. And then I recorded 3, 4, and 5, and those are posted. I will admit, I put 4 and 5 together in one. And when I did the lecture, and then I went to swap over to do the problems. And when I did the swap, I somehow like froze the screen. And so like for 2 minutes, it's a black screen and I'm talking like it's all working and it's not. And then I realize it in the video and then I go back and show you everything. So I know that there's a black screen for a little while and I'm sorry, but I don't know how to edit videos. So it is what it is. And I wasn't going to start all the way over. So I apologize, but just stick with it. Just follow through and I'll get there. Okay, y'all have any questions? Y'all doing okay? Yeah? Yes, ma'am. It is still, the exam is still going to take you the same normal amount of time. It will be 33% from each chapter. So I'm not making it longer. It is still going to take you the normal amount of time. I don't want you to freak out and I'm going to make it another, I don't know, 50 minutes or something. I'm not. So I'm making it right now and trying to make sure that I get a balance from all the chapters, but that it doesn't take you longer than it should. So it'll be about the same length. I can't tell you number of problems because that depends on what style problems, right? You know, the more math problems you have to do, the shorter the exam is. Make sense? Yeah, okay. Yes, we're gonna do clicker questions. We are gonna do clicker questions. I'm sorry, I did not look at the chat. Oh my gosh, y'all, I'm so sorry on the chat. But we're about to start clicker questions. So if you have a chat question, please ask me. I'm gonna look at the screen now. I apologize. Okay. Where? I did pull them up. I believe I did. Nope, not that one. I thought I pulled it up and pulled up the ones I wanted, but apparently I didn't. Okay. Y'all are so sweet. And patience. So we're going to start off with a little review from our carbohydrates from chapter 6. So put on your remembering caps, and I think we're starting, yes, here. Okay, so this was the last one we did last time, I do believe. We were looking at chiral centers. All right, the structure of sorbitose is shown below. Select the correct classification. So select the correct classification. And I'll give y'all a minute and a half. Ten seconds. Okay, y'all run in. Okay, so tell me, what do I have in this molecule? Everything is either a keto, or an aldo. So we either have a ketone or an aldehyde. Which one do we have? We have a ketone. So here's our carbonyl carbon. We have a carbon right there. How many things is it attached to? How many different carbons? That's 1, 2 carbons. So that is a ketone. Remember, lock and key, you need 2. So we can get rid of our aldehydes. Now, what should we do? So either you can look at the D and L, or you can count your carbons. Let's count our carbons. 1, 2, 3, 5, 6 carbons. So 6 is what? Hex. So we're either A or C. And then we're looking at our hydroxyl group farthest away from the ketone. And so are we on the left or the right? We're on the left. So it is the L designation. So it should have been C. Okay. Well, I'm looking at the wrong thing. I'm like, where's my, it's up here. All right. So, oh, what did we say it was? C. Okay, so we were getting close. We were getting close. All right, let's try another one. Select the correct classification. Oh, my microphone's cutting out. Select the correct classification for this monosaccharide. My hands are so cold. Usually have pockets. I can put my hands in my pockets. Can't do it today. Okay, I'll give you 10 seconds from now, so 138. Sorry, I wasn't looking. So 138. Okay, so 47. All right, so what do we say? Is this a ketone or an aldehyde? It's another ketone, so we can get rid of our aldehydes. How many carbons? 6. So we are another what? Ketohexose, right? We can eliminate those. Why didn't we have to say the D or the L? Is there an orientation on this one? Yeah, we're on the right side. It did give it to you here, but why don't I have to list it in my answer? If I don't put something, what do we assume it is? We assume it's D. So if it's not listed, you can assume it is D. Okay. All right, so D, it should have been D. Good. All right, so now I want you to look and see if you can identify the glycosidic bond in lactose. What is the glycosidic bond in lactose? Oh, thank goodness that shut off. The air conditioning just shut off for those of you on Zoom, and we're all happy. Okay, 10 seconds. Okay, so 46. All right, so, oh, Haley, you have a handheld clicker or a? Close it out, like completely swipe it up, get rid of the program on your phone, and then reopen it, and I bet it fixes it. Okay, so when we're trying to identify this, what kind of carbon are we looking for? Looks like D and B. Oh, D and B are the same. Oh, okay. Thank you, Jason. So what are we looking for when we're trying to identify glycosidic bonds? The carbon attached to 2 oxygens, which is the anomeric. N-I-N-O-meric. Right. Okay, so the anomeric carbon. So this is the anomeric carbon that's actually participating in the glycosidic bond. I don't know, I'm going to talk about the answers in just a second. Okay, so when we find that anomeric carbon, we look, is there another carbon attached to it down here? We don't have another carbon attached to it, so we start this counting at 1. We don't have to go around and count anymore because that's the one participating in the glycosidic bond. So tell me, is this glycosidic bond right here cis or trans? And cis is beta, right? So we can get rid of these. Now what? Go and number your other carbon, your other monosaccharide. So 1, 2, 3, 4. So you have to get to the one that's participating in the bond with the oxygen. So what do you get? Beta, and then we're going to name the one that's in the glycosidic bond first, beta 1, 4. Okay, so beta 1, 4, right? You cannot write them this way. If you were going to write, if you had more than one carbon that was participating in the glycosidic bond, it would be like alpha beta. 1, 2, right? But don't write it where you separate them. That's an incorrect way to do it. Okay, so beta 1, 4. So your answer should have been A. Good. Ooh, y'all are doing good. Okay, now sucrose. Tell me the correct statement about sucrose. Uh, 5 seconds. But I think almost everybody's checked in. What do you mean? What's that, Jason? Oh. Yeah, that happens. Happens to the best of us. All right, so sucrose. Is it a disaccharide, a monosaccharide, or an oligosaccharide? It's a disaccharide. So look, you can get rid of 2 answer choices right off the bat. That's how you should do on the exam. You should eliminate the answer choices you know are wrong right away. Now, you have to know what the 2 other monomers are. Are they glucose? Are they fructose and glucose, or galactose and glucose? They're fructose and glucose. Okay, so that should have been B. Good. Very good. All right. So why are oligosaccharides important? Why are oligosaccharides important? Okay, 10 seconds. Okay. So tell me, first off, what is an oligosaccharide? How long? Remember, there's mono, di, oligo, and poly. Mono is 1, di is 2, oligo is 3 to 9, poly is 10 and greater than 10, anything greater than 10, right? 3 to 9, good. So What are the main structural materials in plants? What's the name for that? Do you remember? Starch is the main energy source in animals. Cellulose. Remember cellulose? Maybe not. Is cellulose and starch, and the main energy source for animals is glycogen, right? Energy form storage for animals, glycogen. What are all those things that we just listed? Cellulose, starch, glycogen. Are those oligosaccharides? What are they? They're poly. They're all polysaccharides, right? The only answer choice that was actually an oligosaccharide is D. So oligosaccharides on cell surfaces allow immune cells to distinguish a person's cells from the cells of another organism. So why is that important? For our blood type. So if you're type O, not a typo, T-Y-P-E, type O, how many saccharide units are in that signaling molecule? You have 3, right? If you're type A, how many do you have? You have the same 3 plus 1, so you have 4. If you're type B, you have the same 3 as type O, but you have another one that's different than type A. But in total, you have 4. What if you're type, AB? You have 4 and 4, right? You have the A4 and you have the B4. Yeah? Remember this? Okay, so that one was correct. Okay. So now, why did somebody pick E? Don't pick E. There is no E. Now that you kind of remember blood types, my last question to you is on blood types. So select the false statement in relation to the blood types. Last one. And then we got to move on. But it made it easier, didn't it? Y'all complain during, but after y'all are always happy. You know more about blood types than we'll go into here. Look, everybody's had me in the past from high school. They're all nodding their heads. Like, we've been there, we know this stuff. We went into it pretty deep. Because we did the RH factor as well. And here we're only doing ABO. We're not. All right, about 10 seconds, y'all. I always liked the blood unit. I always thought that was cool. Sprinkles, donuts and sprinkles, man. Donuts and sprinkles. All right, here we go. All right, so individuals with type O blood can donate to anyone. True or false? That one's true. Individuals with type A blood can donate to anyone. That one's false. That one's false. Individuals with type AB blood can accept blood from anyone. That's true. They're called the universal recipient. What do we call type O? Universal donor, right? Because everybody has these same type 3 saccharide units, right? Oh, the false statement. I know. Individuals with type A blood have type A markers. True or false? That's true. A has A, B has B, and then AB has both A and B. So they're all correct except for B. Individuals with type A blood can donate to anyone. Who can type A donate to? Type A and type AB. Very good. So you can give to yourself or anybody who has what you have, right? Okay, so that should have been B. Y'all are doing great. Awesome. I think we did good on clicker questions today. I think y'all did really good. All right, I'm trying to, all right, so let's change gears. Let's go talk about forces inside of substances. Like, no, there are two things that you have to remember for the gas laws for this first section. It was a massively long section. It was, I know. There's one big formula you have to remember. What's your one big formula you got to remember? PV is equal to nRT, piv nert. You got to remember piv nert. It's just fun to say. Just like say it randomly, piv nert, right? Okay, the other thing I told you in the video you have to remember to say, I'm going to put my peas and vegetables on the table. If you remember those two things, you're going to be okay. Okay, so peas and vegetables on the table and piv nert. Those are our two things, yes. Okay, everything else is on your equation sheet that's in the materials for the exam. I'm going to give you a really big suggestion. When you are doing your homework, when you are doing any practice problems, print out or pull up that page on your computer. That way, when you get to those problems, you know where to go and find the information that's on those pages, right? It won't be you looking for them on the exam. You're going to know where they are because I'm not going to change that file, okay? That make sense? So in our first problem here, we're converting from whatever pressure unit to PSI or to ATM. Well, I wrote the conversion factors up here, but where are those conversion factors? Do you have to memorize them? I don't memorize that, right? They're on the page, but you have to know where to go to find them or it's going to take you a long time on the exam. So I'm trying to show you places to save time. And one of those things can be when you're looking for information, right? Know where to go. Okay, so, oh yeah. So I'm trying this on a different program. See if this works better. I don't know. Okay, convert the following barometric pressure readings to ATM. So if I have 1,100, I did this on the thing, 101,331 pascals. Remember I said dimensional analysis wasn't going away? I wasn't lying. So whatever unit you have on the top is what you want to go on the bottom. And I want to get to what? I'm going to get to ATM. So I'm going to put my ATM on the top. It's terrible ATM. What's my conversion? In one ATM, I have 101,000, how many? 325? 325 pascals. So what do you get? It's a pretty close number. Like you should kind of be eyeballing this and going, wow, that should be pretty close to 1. So what do you get? 1.000. How many sig figs do we need? It's a really great question. Well, so a lot of times we give ATM in only one significant figure, but technically we're supposed to give 6 because you don't base your significant figures on conversion factors. You base your significant figures on the original values that were given. So I would accept it as either 1 ATM or 1 point, how many zeros do I have to go? There's 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 significant figures. Oh, the last zero would be a 6. Sorry. Thank you. All right, so that would be ATM. Okay. All right, how about B? 762 millimeters of mercury. And that's what's in a blood pressure cuff. If you've ever seen a blood pressure cuff and seen the dial, the units on the dial of a blood pressure cuff are millimeters of Hg. So we're going to put that on the bottom and we want to go to ATM. So what's our conversion? In 1 ATM, we have 760 millimeters of mercury. So what do we have? Yeah, we should have something close to 1, right? Is it 1.00? Yeah, because it's 3 significant figures. And don't forget to put your units, 1 ATM. Okay, and then C, 14.6 PSI. You're right. Look, Abigail's already ahead of us. We have 1 ATM, and in 1 ATM, we have 14.7 PSI. We need 3 significant figures, so what do you get? 0.9, I got 9.3. Is that what you got? Yeah. So 3 sig figs, 0.993. Okay. Oh yeah, and I'm doing this, I gotta clear it every time I go to the next problem. Okay. Suppose you have the same amount of gas in 2 containers, C and D. Both containers are at the same temperature. Container C is half the size of container D. Which gas is at higher pressure? I want to show you with the formula, and then we'll kind of talk about it. But let's use our PivNerd. I'm telling you, if you write PivNerd and peas and vegetables on the table when you get your exam, just so that you know if I get to a gas problem, I'm going to use one of these 2 things, and you're not hunting around for a formula, it's going to help you a lot. Okay, so PV is equal to nRT. So what we're doing when we go from C to D, so both containers are the same temperature, okay, so we don't have to worry about that. Container C is half the size of container D. What does that mean, half the size? What parameter inside of PivNerd are we referring to? Volume. So does our volume go up or go down when we go from C to D? C is half the size of container D, so volume goes up, right? Okay, if I keep everything else in my equation constant, if my volume goes up, and I know that my temperature is going to be constant, my R is a gas constant, right? So it's never going to change. That's the gas constant. They didn't change the number of particles. So N is our number of moles, right? We have the same amount of gas. So we have the same number of moles. So that's all constant. If I change volume, what's going to have to happen to pressure? So we want the 2 sides of the equation to be equal, right? So put this set to any number, pick a number, 50. If I increase volume to make this equation still equal, I'm going to have to decrease pressure. Does that make sense? Yeah? Okay. So all it is, if you're just thinking about what do I have to do on one side of the equation or the other to make it still equal, you can do it. So that would be your answer. If it were multiple choice, like what would happen? Well, pressure would drop. When you're going from C to D, pressure would drop. The other way that you can think about it is you have the same number of moles. So you have the same number of particles, right? So let's say I have 1, 2, 3 particles. And I went from C to D and my volume doubled. I don't think that's really doubling, but that's okay, right? I still have 3 particles. The definition of pressure, P-R-E-S-S-U-E-R, pressure, no. Pressure, E-U-R, I don't know, pressure. I'm just having a day today. All right, your pressure is really the number of times, thank you, Jason, number of times particles strike the side of a container. S-S-U-R-E, U-R-E, that's what it was, U-R-E. Okay, that's what I was having problems with. So tell me, in container C versus container D, where are we going to strike the wall more often? In C. In C, we just have so much more space in D that we're not going to run into the sides of the wall as often. And so if you increase the volume, you're going to decrease the pressure. So you could think about it either way. Either way is perfectly fine. I just want to show it in both to you. Okay. Yeah, I got to clear this. I got to clear the ink. All right. Now here's one that gets a little bit complicated. When you swim underwater, the pressure of the water pushes against your chest cavity and subsequently reduces the size of your lungs. For every 10 meters below the water surface, the pressure exerted by the water adds 14 psi to atmospheric pressure. So the total pressure 10 meters below the surface would be 29.4 psi. Where did they get this number? If you're at 10 meters below sea level, how did they get 29.4 psi? You're always going to start with atmospheric pressure. What's atmospheric pressure? 1 atm, which is also 14.7 psi, right? But that's only if you're like standing here like we are. But if you stood here and we were like in a pool, right? And we went 10 meters down, we would have that total atmospheric pressure plus 10 meters of pressure from being underwater. So how much pressure do you get when you go 10 meters down? Plus 10 meters of water from the problem. For every 10 meters below the water surface, the pressure exerted by the water adds 14.7 psi. So what's our total? 29.4 psi. So y'all see where they got that 29.4 psi? I think that was a confusion last class. Well, it doubled in 10, but then it won't quite be a double when you go to 20, right? But it's every 10 meters, you're going to add 1 atm of pressure. Okay? All right. So now let's try to solve the problem. So if we have a lung volume of 6 liters at sea level, that's atmospheric pressure, what would the volume of your lungs be when you are at the bottom of a pool that is 5 meters deep? So that's a lot of information in this one problem. But what I can tell from this problem is that I have an initial condition and I have a final condition, right? So I'm going to start picking out that information. Let's do initial first. So let's do initial at sea level. So at sea level, I had initial volume of what? VI, that's a little I. What do we have? So sea level is our initial condition. We have 6 liters. Okay? And what's my pressure? It says I have a lung volume of 6 liters at sea level, atmospheric pressure. What is atmospheric pressure? Atmospheric pressure is 1 atm, which is also 14.7 psi. That is correct. Okay, now they're saying, what would the volume be? Okay, now that means I'm changing conditions. I'm at 5 meters deep in the water, right? So I want to know, what would the volume be? Volume final is our unknown. What's my pressure? This is a little bit tricky. What's my pressure? Okay, so how did you get that? So we know for 10 meters of water, it's 14.7. So 5 meters of water would be 7.35 psi, right? Yes, so we divide by 2. So now we have to say my pressure at 5 meters is my 1 atm, right? That's my atmospheric pressure of 14.7 psi plus my 7.35 psi from the water. So that's from 5 meters of water, and this is from the atmosphere. ATMOSPHERE. So you get 22.0. So you're going to get 3 sig figs, PSI. I was doing great. Okay, so do I want to use PivNerd or do I want to use peas and vegetables on the table? Peas and vegetables on the table. Peas and vegetables on the table. Yeah, I didn't think y'all would be talking about peas and vegetables on the table, huh? Okay. Which one of those conditions do we not have to worry about? Temperature. So you can just scratch that sucker out, right? But do you have to know which law it was to solve the problem? No, which I don't like about the way your book does this, is that they want you to know the laws before you understand how it works. Understand how it works first. Okay, so our pressure initial, we said, was 14.7 psi. Our volume initial was 6 liters. Our pressure final, y'all told me 22.0 psi. And then our volume final is what we're solving for. So we divide by 22.0. 22.0. So what do you get for a final volume? What'd you get? 0.3? So your least significant figures is a 6. So you can only have one significant figure in your answer. So if it's 4 point something, you should round, right? 4 liters. Oh, my units. Hello. Units would be nice, right? How could you check your answer? Remember PivNerd. PV is equal to. Like, why won't it erase there? PV is equal to nRT. What did we change in this condition? We changed our PSI from 14 to 22. So our pressure went up or down from initial to final. Our pressure went up. So if our pressure goes up, the question is, what's going to happen to volume? It's going to go down. Did it? Yay. Y'all did a great job. Ooh. It's a good way to be able to check your work without having to really know. All right, a gas has a volume of 10 liters at 0 degrees Celsius. What is the final temperature of the gas? Okay, so that must have been initial, right? So VI, TI. So what is the final temperature? Temperature, we don't know. If it's volume final, increased to 25 liters. So T final is our unknown. What do you notice first off the bat? There should be a real big red flag for you. Celsius. You're always going to want to convert to Kelvin, because when you write PivNerd, PV is equal to nRT. This constant right here, its units include Kelvin. And so if you don't put it into Kelvin, none of your math is going to work out. So always, 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 always put it in Kelvin. And do y'all remember what I said in the video? I'm not going to be really mean to you like the book was. Up here, they gave you Fahrenheit and then wanted you to convert from Fahrenheit to Celsius and then Celsius to Kelvin. It's like, oh my gosh, no, that's crazy. So I will expect you to convert from Celsius to Kelvin, but not from Kelvin, not from Fahrenheit to Celsius to Kelvin. Okay? So how do we convert from Celsius to Kelvin? 273, right? So where did you get that number? Because you're going to take an exam and you're going to need that number. Where was that number? In the back of the book or on that sheet, right, that I posted for the exam. It's there. You need to find it. You need to be able to find it. You don't want to draw a blank on an exam and go, oh my God, I just can't convert from Celsius to Kelvin, right? Know where it's at. Okay, so this is 273 Kelvin. All right, but we want to give our answer. What is the final temperature in Celsius? So we'll have to convert it back when we're done. Okay, so peas and vegetables on the table, right? So what do we got? Our pressure, oh, we don't need pressure. We can just kind of get rid of pressure, right? So now we're really only worried about volume and temperature. So our volume was 10, Dr. B, put your units, 10 liters. Temperature was 273 Kelvin. I don't know what's going on with this mic today. Volume, oh, I didn't put my I's and F's. Temperature, I'm sorry, volume final was 25 liters and temperature final is what we are looking for. So cross multiply, because you got to get temperature final on top, right? So you're going to get TF times 10 liters is equal to 25 liters times 273 Kelvin. But then you're going to have to divide by 10 liters. So what do you get? Temperature final. $682, is that what y'all get? We want, how many sig figs? We want, see now, you only really get one significant figure, which is kind of crazy. We'll do it in the same sig figs as we had here. So we'll do it in 3, even though you really should only give 1. So how do we do that? Subtract 273. So what do you get? 400. No, what is it? 412? 10 Celsius. That's only 2 significant figures, but yeah. Usually you go to the ones place. For Celsius, you go to the ones place. Okay. But I'm not testing you on significant figures on this exam, right? Okay. Assuming no air can move in or out, what happens to the volume of a hot air balloon as the air is heated? Y'all have seen hot air balloons before, right? And they have a little fire underneath, and when they want to rise, they crank up the heat. Okay, so let's see what happens. What formula do we want for this? We want PIV-NERT or peas and vegetables on the table? All we're asking here is what happens to volume, right? So let's use PIV-NERT, right? So what happens to the volume? My question is, what happens to volume when air is heated? So when my temperature goes up, if I want both sides of the equation to equal each other, if I increase something on one side, what do I have to do on the other? I have to increase it as well. Isn't that so much nicer than memorizing 6 different formulas for gas laws? Like, don't do that. Know the little sayings that I gave you so you know who's who. Like Boyle's law, right? What is Boyle's law? He saw a boil on his face and he was peeved. So it's pressure and volume, right? Know those little tricks. All right. Okay. Oh, this is good. And okay, so when you have a patient, right, who's not breathing on their own, you use one of these on them. It's called an ambu bag. So why do you use this? When you squeeze that bag and it's covering the patient's mouth, what's going to happen to them? You're going to force air into their lungs, right? So how does that happen? Well, squeezing the bag decreases the volume, right? So inside the bag, if we decrease the volume, PV is equal to nRT, right? If our volume goes down, what's going to happen to the pressure? Going to have to increase, right? Because we're on the same side of the equation. So what happens to the pressure inside the bag? The pressure inside the bag goes up. How does this help a patient who's not breathing on their own? What does it do for the patient? It forces air into the patient's lungs. And now you have to realize that inside of this thing here are lots and lots of valves, right? Because if you squeeze that bag, it's going to force air into their lungs. When you relax the bag, you want the bag to fill up, but you don't want it to fill up with what they exhale, right? So there's a valve that will release that air into the air, release that breath into the air, and then it will pull either fresh air, or if you have it hooked up to an O2 tank, right, it'll give them a higher percent O2. It just depends on the setup. So there's a lot of valves to make sure that that happens properly. It seems super simple, but it's actually a lot of valves. If anybody's interested, I can like send you a video on how it works. Kind of cool. But my idea of cool might be different than other people. I've come to that realization. All right. We have a 100 milliliter bubble of hot gas. So I'm going to know that that's a volume. That's 100 milliliters. And it is at 225 degrees Celsius. So that's a temperature. Oh, and a pressure. And at 1.80 ATM, right? Okay, so that's kind of one condition. And it escapes from a volcano. Ooh, this sounds like fun. What's the new volume? So the new volume is going to be our final. So these were all of our initial. What's the new volume where the temperature is minus 25 degrees Celsius and the pressure, I'm running out of room, is 0.8 ATM? What do we have to change first? Celsius to Kelvin. So this is why you have to do this. So 273, what do you get? 498? Okay. Then we're going to do it over here, plus 273. Now be careful, this is a negative 25. If you plugged in a negative 25 into our problem, we would end up with a negative number, and we can't have a negative number. So all of our calculations have to be done in Kelvin because you can't have a zero, you can't have a negative temperature, right? In Kelvin, absolute zero is the coldest anything could ever be. It cannot be colder. It's where you have absolutely no particle movement, and we've never actually seen that. And so you'll never have a negative number. Okay, so what do you get? All that for this. 248. Okay, so what am I going to use? Peas and vegetables on the table or Piv Nerd? Anytime you have multiple conditions, you have an initial and a final, put your peas and vegetables on the table. Okay, peas and vegetables on the table. Good. Peas and vegetables on the table. Anybody else has ever been taught the peas and vegetables on the table? Anybody? No? Oh. Just curious, like how other people teach it, you know? Okay, so my pressure initial was 1.80 atm. Volume initial was 100 milliliters. Do I need to change milliliters to liters? No, just so long as you realize that if you're solving for volume, you're going to get out a unit of milliliters instead of liters. Okay, and then my temperature initial was 498 Kelvin. So my pressure final, 0.8 atm. My volume final is unknown. And my temperature final is 248 Kelvin. So volume final, just do your reverse 0.8 over 248. So that cancels and that cancels. So over here, 248 over 0.8. Lots of math. So what do you get? I see people writing. What y'all get? Something in milliliters. I got 112. Is that what y'all got? We good on that? Make sure you can do that math, because you have to make sure you know what goes where when you're moving things around. Okay, so be careful with that. Don't get it wrong just on the math. All right. Okay. As a cylinder of compressed gas empties, the pressure inside the cylinder decreases. Explain why this happens using the ideal gas law. So you can think about like a tank of propane that you get for your barbecue pit, right? That's a tank of gas under pressure. So what happens when you empty it? You turn the knob, right? And so gas is going to do what? Gas is going to leave the tank and go to your barbecue pit so you can enjoy your steaks on the grill, right? I could use a steak on the grill. That'd be nice. All right, so what's going to happen to the pressure? Oh, it's telling you the pressure inside the cylinder decreases. Explain why this happens using the ideal gas law. So PV is equal to nRT. So as our pressure decreases, does our volume change? No, our volume is constant. So constants. Volume, right? Because it's a cylinder, it's a tank, it's not going to change. It's not like it's a balloon. This is a tank that's not going to change. How about temperature? Is our temperature going to change? No. And our gas constant, is our gas constant going to change? No. So why does the pressure decrease? Because what escapes, Jason? Jason's on the track. The amount of gas flows out. So those gas particles are an amount of something. What variable in Pivner tells us the amount of something? Moles. Because the number, good job, y'all, of moles in the tank decreases. Right? So if on one side of an equation, our number of moles goes down, what happens to our pressure? Our pressure is going to go down. I'm like an icicle by now. Okay. We good on that one? Can I clear that one? Yeah? I hear the page turning, so we must be okay. All right, now we've moved on. Finally, we've moved on from gases, right? We can finally get to liquids and solids. So on Thursday, we're going to talk about some biologically important molecules. But in order to understand those biologically important molecules, you have to understand the attractions that happen between all molecules. So that's the first thing that we're gonna do. So when we talk about this, y'all know about ionic bonds, right? That's an exchange of electrons. How about covalent? What's a covalent bond? A sharing of electrons, right? Now, are bonds and attractive forces the same thing? No, they're not. So in bonds, you're either going to, I love the big NO, that's exactly right. No, they're not. In bonds, electrons are moving. Electrons are exchanging places. So that's how you define a bond. In an attractive force, you're going to have an attraction between oppositely charged things, right? Like magnets of different polarity are attracted to one another, right? It's that sort of attraction. So be careful with bonds and attractive forces, especially my least favorite attractive force, because it was named so improperly. Can you guess? Hydrogen bonds. Are hydrogen bonds bonds? They're not. Whoever did that, bring them to me, I will shake them. That's crazy. Why would you do that? Why would you do that to all these students, right? It's not a bond. They call it a hydrogen bond. It's not a bond. Not a bond, okay? So get that. We get that out of our systems. You know, Dr. B's book of pet peeves, hydrogen bonds at the very top. Super important, but named incorrectly. Okay, so what type of attractive force, not bond, but attractive force exists in all molecules? These are London dispersion. Forces. Oh, they exist in all molecules, but they're the weakest. So they're the weakest. Why are they the weakest? They're the weakest because they're temporary. They're a temporary shifting of the electron cloud. Electron cloud, right? You can have a perfectly nonpolar molecule, perfectly nonpolar. It bumps into something, it temporarily has a partial positive and a partial negative charge. And then a second later, it goes back to being nonpolar. Even less time than that. That's a London dispersion force. Now it occurs in every single molecule. No matter what kind of interaction is going on, if it's hydrogen bonding, if it's dipole-dipole interactions, doesn't matter. You're going to have London dispersion, but we don't talk about it because it's very weak and the other forces are stronger and therefore have a bigger impact on how the molecule will behave. Okay? All right. Whoop. Come on. All right. Given that only polar molecules can participate as donors in hydrogen bonding. Oh, let's back up a second. Let's talk about hydrogen bonding for a second. If you're going to have a hydrogen bond, what two things do you need? You need a donor and an acceptor. Okay, so Hydrogen, Jason, is hydrogen our donor or our acceptor? And it could be anybody. I'm not really picking on Jason. It's going to be our donor. So it's a hydrogen, but it's not just a hydrogen. It must be a hydrogen that is what? That is in a covalent bond with what? And this is my funny part. With no fun. Now remember that from the video? No fun? Hydrogen bonding is no fun, right? Because you have to have a hydrogen that's in a covalent bond with no, which is nitrogen, O for oxygen, or F for fluorine. No fun. Okay, so tell me about this acceptor. What about the acceptor? The acceptor must have a lone pair of electrons on what? No fun. Nitrogen, oxygen, or fluorine. Because you have a lone pair on either nitrogen, oxygen, or fluorine, that means that you're going to have a polar molecule. So can you have a polar molecule that does not participate in being a hydrogen bond donor? So given that only polar molecules can participate as donors in hydrogen bonding, is it true that all polar molecules can be hydrogen bond donors? What do y'all think, true or false? Could I have, let me show you an example. Could I have, is this molecule polar? That's that first. Do I have polar bonds? Carbon and hydrogen, are they polar bonds? No, right? That was our exception. Carbon-hydrogen bonds are never going to be polar. How about carbon-chlorine? Is that a polar bond? It is a polar bond, and chlorine's really close to fluorine the floozy, right? So chlorine's going to steal those electrons from carbon. So we're going to point at chlorine. Well, here's another chlorine-carbon bond. So I can look at all of the polar bonds in my molecule and see, is this molecule polar overall? This is really important. This is what we did. I don't remember what chapter this was. But what's going to end up happening is you have an overall polarity of the molecule where over here is partially positive, and then over here is partially negative. It's a partial charge. It's not a whole charge, but it's partial. Right? So we do have a polar molecule here. Now, can this polar molecule participate in hydrogen bonding? Why not? It can't. You're right. You're absolutely right. It cannot. Why not? Well, because we don't have a hydrogen, we're asking about a donor now. So because that hydrogen is not bonded to a nitrogen, oxygen, or fluorine, it's bonded to a carbon. So that hydrogen will not act as a hydrogen bond donor, okay? And then it cannot act as an acceptor either because we don't have lone pairs on no fun, right? Okay, so now that we kind of have an idea of our hydrogen bonds, Considering our answers, can water and carbon dioxide form a hydrogen bond? Take a second right now, draw water and carbon dioxide. I'm not going to do it. You do it. Draw water and carbon dioxide. Which do they look like? Okay, so your water, you should have ended up with something that looks sort of like this, right? Because we know water is a bent structure because it has two lone pairs on it. Okay, how about carbon dioxide? Carbon's going to be in the middle. We'll have oxygen on either side, but does carbon have a complete octet? No. So there's no other atoms there, so we have to make double bonds. So carbon's got a complete octet. How about oxygen? Oxygen doesn't either. So we're going to have to put a lone pair, two lone pairs on each of our oxygen atoms. Okay, now the question is, can carbon dioxide and water form hydrogen bonds together? Yes or no? So tell me a yes or a no. So if we look at water, water has two hydrogens that are partially positive, right? If we look at our electronegativities, we know that oxygen has a greater electronegativity than hydrogen. So these hydrogens are going to be partially positive. So these hydrogen atoms act as acceptors or donors? Donors. So we have two donors. Now, what else do we have in the water molecule? Two lone pairs. So these are each acceptors. So water has the possibility for 4 hydrogen bonds. Now let's talk about carbon dioxide. Do we have any donors in carbon dioxide? We have no donors, but what do we have? We have acceptors. Yes, we have lone pairs. So these are acceptors. So yes, you can have hydrogen bond formation between, and I guess I should have done those in black because I was doing the acceptors in black, right? Those are the acceptors. So you can have a hydrogen bond, absolutely, between, and you kind of do them as dashes, between an acceptor on one site and a donor on another molecule. Thank you. All right, so you can have hydrogen bonds anytime you have a donor and an acceptor. Y'all check y'all mics. Make sure you're not. I don't even know how to check that. I don't even know how to do that. I think that's participant. There we go. There we go. Okay. All right. So anytime you have a hydrogen bond donor and a hydrogen bond acceptor on 2 different molecules, you can create a hydrogen bond. All right. So then this donor could interact with another carbon dioxide molecule with the oxygens, the lone pairs on the oxygens. Okay. Name 2 functional groups that contain ionic charges. Remember, ionic interactions are a type of, the strongest type of interaction that we've been talking about. So, and remember when I said functional groups aren't going away? I did warn you. I did warn you. So, functional groups. Anybody have ideas? I'll give you a hint. One of them starts with something you already know. What is this group? Amines is correct. We're going to get to amines. What is this? This is a carboxylic acid, right? It's carboxylic acid. Now, what happens if I take away this hydrogen? What do I end up with? Oh, a charged molecule, right? What do we call that? Very similar, a carboxylate, a carboxylate. And then the other one is an amine. But it's a specific kind of amine. It's a protonated. P-R-O, protonated. What does protonated mean? A proton is a hydrogen, so it's got an extra hydrogen. Something is protonated that has an extra hydrogen. Okay, so our protonated amines, an amine always has a nitrogen, right? So it's going to have a nitrogen and some number of hydrogens attached to it. If I have one R group, and if I'm not protonated, it would be an NH2, but in the protonated form, it's an NH3, and it has a positive charge. What do we call this? A primary, secondary, or tertiary amine? This is a primary. Primary. So what if I had two R groups and only two hydrogens, and I was a positive charge? Secondary, and then it would be R3, if you can read that. One hydrogen, and it's still protonated, still positive. This would be tertiary. And I see I am out of time. The last two sections, the last three sections are really short, so we'll catch this up on Thursday. We'll absolutely catch this up on Thursday, okay? All right, take a big deep breath. Y'all got this. You got this. All right, I will see y'all on Thursday. Anybody on the chat have any questions? Let me write down as far as we got so I remember tomorrow. So we got to here. Okay, if nobody has questions on the chat, I'm going to go ahead and end the Zoom. Y'all have a great afternoon.